Okay, so let's have the next one. So air undergoes an isentropic compression from 0.31 Newton. Again, that's a typo. That is a square centimeter to 3.87 Newton square centimeter again. So if the initial temperature is 20 degrees Celsius and the final temperature is 327.5 Celsius, what is most nearly the work done by the gas? So we are looking for a work done now. Okay, so we already have a K equal to 1.4, and we already have here says in the problem stating the problem is compression. So we already know that the work must be negative because it is compression process. Okay, so compression negative, if it's expansion, it should be positive. So we are already expecting a negative answer. Negative final answer. Okay, so writing down again the givens, we have P1 is equal to 0.31 Newton per square centimeter. And then, it, no. Okay, so I just write P2, 3.87 Newton per square centimeter. And then, what else? Oh, we have T1 and T2, right? So T1 is equal to 20 degrees Celsius and T2 is 327.5 Celsius. So we are asked to find what? Oh, we are asked to find the work done. Okay. We still have the value for K. K is the adiabatic constant, right? Now we are required to find work done. So we are expecting this to be a negative. Okay. And maybe in joules. Okay, so it should be in joules. Now required, no, not required, sorry. Solution. So for the solution, we have work. This form, I already discussed this formula earlier also. So MR times T2 minus T1. T2 minus T1 all over 1 minus K. So the problem here is we don't have the value for R, right? But and we don't have the value for M. But M is easy because what you can do here is you can consider M as 1 kilogram. Why? Because there is no given a volume, no? There's no given volume. But if there's a given volume, maybe you can use the volume density formula and find the mass itself. But however, for this one, you don't have any given for the you don't have any volume given. So we can just consider that M is just equal to 1 kilograms. Okay. So the problem here is R. So you have to consider here, or don't forget, remember that we are dealing with air. So air undergoes an isentropic compression. So we are looking for the R of air. So that is the one that we need to find. Okay, air. Now what is the R of air? Okay, so let's find the let's solve for R first, okay? So we have to solve for R first, okay? So R is equal to generally, right? The R, no, this is not R. The R asterisk. This is 8.314, right? 8.314 joules per mole Kelvin. Okay, so this is your R. This is not yet your R that we should be using, okay? Because we have to consider first, we have to consider that this is air. Okay, but we all know that R is equal to R asterisk over molecular weight, right? Of air, molecular weight of air, of course. Now, what you can do here is molecular weight of air. What is the molecular weight of air? So this is the important thing that you know is that is 29. Okay, 29 gram per mole Kelvin. Okay, no, sorry, gram per mole. And if I will make this into kilograms, that's 0.029 kilogram per mole. Okay, and then what else? So therefore, R is just 8.314 over 0.029. Okay, and then this is the R for the air. And the answer for this one is uh, 287. And what is the unit? Okay, let's put the units first so we'll be able to verify what is the unit for this one. So this is joule per mole Kelvin over kilogram per mole. Okay, so cancel mole, okay, we can cancel mole. Therefore, for this one, this is approximately equal to 287 joules per, okay, kilogram Kelvin. Okay, so this is the air. Even if you search it in the internet, in your browsers, you can just search the molar gas constant for air. Okay, so you'll be able to see the results as to approximately 287. Okay, so that is how you got the 287, if in case you are wondering. So that is the derivation. So now going back to the original formula, so to the original equation, we have mass, right? mR. So 1 kilogram. So R is this one, 287 joules per kilogram Kelvin. Okay. And we have T2 minus T1, right? So what are the T2 minus 1? That's 327.5, okay, minus 20. So that is in Celsius. So it's fine because we are dealing with change in temperature, right? So again, this should be also equal to Kelvin. So that's fine. You don't have to do any conversion here anymore. And all over 1 minus k. So 1 minus 1.4. Okay, so solving this one to your calcu, you should be getting, as you can see, the denominator already indicates a negative value. So negative 220.27 kilojoules. Okay, so again, that is a negative that indicates a compression. So we're right. So we got a negative final answer. That is the correct answer. So I think that's it. Let's have the next one. Okay, so let's have this one. So we have work of a polytropic, N is equal to 1.21, compression of air, K is equal to 1.4 in a system of moving boundary from P1 15 psia, V1 1.0 cubic feet to P2 150 psia, and V2 is equal to 0.15 cubic feet is equal to what? Okay, so the one that we're looking for is work. Right, that is work. So we have a given of N and K. So remember, N is your polytropic index and K is your adiabatic constant. But since we are dealing with the polytropic, okay, stated in the problem, polytropic compression, so we'll be using N. Okay, so writing down all the uh, values are given. Okay, so again, we have N and K. So we'll be using N because we are dealing with polytropic compression. Therefore, we'll be using the polytropic constant. Okay, polytropic index rather. So we have given P1 and V1. Okay, just write it down. What else? And P2, 150 psi, and V2 is equal to 0.15 cubic feet. Okay, so what formula should we use? Okay, so this polytropic, let me just indicate here so you guys will not be able to forget it, that we're dealing with the polytropic process. Okay, solution, work. Okay, so we are fine. We are again expecting a negative value for work because that is a polytropic compression. So we should be able to know again that the final answer that we'll be getting should be a negative value because that is a compression process again. Okay, so the solution and the formula that we'll be using is again this one. I already discussed this earlier. You can just check it out yourself. We have P2 V2 minus P1 minus P1 V1 all over 1 minus N. Of course, we'll be using the N. We won't be using the adiabatic constant in this case because that is not an adiabatic process. This is a polytropic process. So we won't be using the value for K, the value of K. Okay, so I think we can now um, substitute the values. Okay, so you have to be careful with this one. In thermodynamics, units are very important. So what is P2? So P2 is, okay, that's, okay, so P2 is 150. That PSIA stands for pound per square inch. Okay, pound per square inch, atmospheric. Okay, so but as you can see, the volume is in feet. So therefore, I have to convert this, the inch, the square inch on the denominator into um, square feet. Okay, so converting that, you'll have, there's 12 inches in 1 feet. And of course, I have to square this one. Okay. Uh, so that is your P2. Oh no, that's not yet. We have P2 times V2. Okay, V2 is 0.15. Okay, cubic feet minus. Okay, let me just move this. Let me just fix the line. Okay, there you go. And this should be again 15 pound per square inch. I have to convert this again into feet to square feet. Okay, so 12 inch per, this is squared. Okay. Okay, 12 inch per 1 feet again squared times V1, which is 1 cube. All over 1 minus N, that's 1 minus 1.21. And then, so the final answer for this one, let's check out the units. So inch cancelled, cancelled, cancelled. And then we'll be left with what? Pound, what? 551, negative 5142.86. And the unit for this one is what? We are left with pounds, right? Pounds on the numerator, and do we have something on the denominator? That's pound foot. Yeah, pound foot. Okay, pound foot. Okay, so you can have this as your final answer. Okay, okay. As you can see, again, that's negative. That indicates a compression. Okay, that's it. I think we can have the next one. Okay, so let's have the last example for this topic. We have 3 pound moles of an ideal gas are throttled per second from 9.2 psia to 6.4 psia. What is the entropy change? So the one that we're looking for is entropy, and we have a given of R. Okay, so given, let's write down the givens. So we have 3 pounds of moles. So that is your N. That is the number of your moles, right? So 3 pound mole, or 3 pound moles, 3 moles per second. Is this right? Yeah, I think it's. Okay, I think this is fine because you have per second there. So this is a throttling process, okay? So we have other givens P1, 9.2 psia, and we also have P2, 6.4 psia. Okay. And then what else? Oh, we have a given of R. What that is 1545.33 feet pound. Foot pound per pound mole Rankine. Okay. So how do we do this? We are required to find what? Entropy change. This should be, okay, let me change this one. This should be 3 pound moles. Okay, let me change this one. This should be 3 pound moles per second. Okay, that's it. Now, so we are looking for entropy. Okay, change in entropy. Okay, so delta S. Entropy change. So change in entropy. For the solution, so for the solution, what is the solution for this one? So delta S or change in entropy must be equal to the formula. The formula for this one is, again, I discussed this earlier. So NR ln of P2 over P1. That's it. So minus N is 3 pound mole per second, right? And R, we already have the value for R. That's 1545.33 foot-pound per pound mole runtime. Okay. And we have Ln, which is P2 and P1. We have 6.4 over 9.2. Okay, so canceling out the canceling it out, the units. So we are left with what? The final answer for this one is 1682.0670 foot-pound per um, second. Okay, runtime. Okay. So you can have this as your final answer, and you can still convert this one to the foot-pound into what? That's foot-pound per second runtime. Okay. So you have to use here a conversion factor if you want. Okay. That's 778 foot-pound per 1 BTU. So you can have also that conversion factor, whatever that is available in the choices. So delta S is equal to 2.1620 BTU per foot-pound. Sorry, BTU per second runtime. Okay, that's it. So I think we can move to the next topic.